Again, we borrow most of the concepts from the metal guy. So the structures, they did it. This concept is very old. It's almost 150 years. Done by Waller in 1860. He was doing some testing for metals, and what he saw here that when he applied very low stress on the samples, so the strength here, we start with a very high strength of the material, and by the time it keep degrading, but it reached certain value that is not gonna fail. It just keep constant, and it's not failing anymore. So, and this is how he defined the endurance limit. So if I apply very high stress, the sample will fail quickly. But you need to reach certain low value for the stress, below which there is no damage anymore. So this concept again is very common for metals, but very minimal work has been done for the hot mix asphalt. But again, this concept started in 1860, and it got picked up from our community in 1972. So it took about 100 years. So Mena Souliman and McLean in 1972, they proposed that the endurance limit for hot mix asphalt is about 70 microcracks, and they did several stiffnesses. These lines represent different strength of the pavement. Again, pavement can vary, or the strength of the pavement can vary based on several factors that I'm going to talk about. But what they said that the endurance limit is constant regardless of the stiffness, and this conclusion I kind of disagree with, because I still believe that endurance limit will change by changing the strength of the material. But at least that's how they started. Then this concept traveled all over the world and went even to Japan. When Nishizawa in 1997, he also reported that the endurance limit is about 200 microstrains, and he used he came up with this conclusion based on some analysis for field pavements in Japan. Wu in 2004, he also reported that the strain levels at the bottom of asphalt layer, it ranged from 96 to 150 microstrains, and he got that based on back calculation using the falling weight reflectometer in some pavements in Kansas. Carpenter in 2006, he reported that the endurance limit is about 70 microstrains, and it can go to 100 microstrains in certain cases. But what is interesting in his recommendation here, that endurance limit can be pumped up all the way to 300 microstrains once you modify your mixture by adding polymer or by adding asphalt rubber. So this is here start to show that endurance limit can change or can improve by modifying the asphalt mixtures that we have been using in the last 100 years. So after several researchers have been doing these individual studies, this concept, endurance limit, now became, it was elevated to a national interest, and there was two national projects were totally concentrated on the endurance limit besides the one that I'm working on. These two projects were the NCHRP 938 and 944, and both of these projects, they showed a clear evidence that the asphalt performance is totally different once you apply very low strains. And when I say that, what happens in these two projects is there is something called normal strain levels or low strain levels. So in the regular fatigue analysis that we usually do, we apply very high strains that range, let's say, from 200 to 1,000 microstrains. But what these two projects did, once they decreased this amount of strain or deformation on the sample to 70 microstrains or 100 microstrains, the sample, it wouldn't fail even after 50 million cycles. 50 million cycles. So, and they came up with a summary that there is a mounting evidence that there is an endurance limit for the hot mix asphalt. So now, after I studied about healing and endurance limit, I came to a step that I need to come up with my statistical experiment. So I need to know what are the main factors that I need to study or I need to include in my predictive model. So these are the factors that I used. The binder content. When I say binder content, is the percentage of the binder in the mixture itself. So if you, again, going back to the road, most of the time the binder content is about 5%. That's the binder content. But I was interested to see if I change this binder content plus or minus, let's say 1% or a 0.5%, is it going to change the endurance limit or not? Same thing for air voids, or if I change the temperature or binder type, or even the rest period, which is the most important part. If I put 5 seconds rest period between each cycle versus 10 seconds, am I going to see a difference in the endurance limit or not? So, one of the projects that talked about the effect of the air voids and the binder content was the SHARP A003A in 1994, and they mentioned that at higher asphalt content and lower air voids, this can lead us to a very high fatigue life. Another project was done by Harvey and Tsai in 1996. They mentioned that at lower air void content will lead to a higher initial stiffness and a higher stiffness fatigue life. On the other hand, once you increase the binder, once you decrease the binder content, this will have a lower fatigue life. So here, as you can see, in contrast, higher asphalt content, lower stiffness, but higher fatigue life. So again, it's a matter of once you increase the viscous part or the flexible part, which is the asphalt, the material will be more flexible and it's going to take much longer to fail. Same thing for based on Tayyip Ali in 1994. He mentioned that once you increase your air voids, this will decrease the fatigue life. Again, imagine that you have any sample. Once you keep increasing the air inside it, it's going to be much weaker. So the fatigue life will be much smaller. So at least now I know that there are two factors that they are important for me to study: the air voids and the binder content. Moving on to the another two factors, temperatures and binder content. Ponar in 1982, he mentioned that at higher temperatures or softer binders, this will result in a higher fatigue life. Verstatrin in 1977, he also performed some fatigue testing for different temperatures, all from -5 Celsius to 15 Celsius, and he concluded that at higher temperature, this will give more benefit in healing compared to lower temperatures. Moving to the other factor, which is the rest period, and this is the most important factor in endurance limit. Ponar in 1982 also, what he did, he applied a rest period and between the cycles, exactly close to what I'm doing right now. And what he said, he have an increased fatigue life up to, I think, 10 times. So if I apply a continuous test, when I say continuous test, there is no rest period. So this can fail the sample, let's say, in 1,000 cycles. If I apply a rest period, it can go to 25,000 cycles, 25 times. So, but something interesting that he mentioned here, that he said maximum, the rest period will reach, you will get the maximum healing possible by applying the rest period equal to 25 times the loading ratio. And let me stop here and explain. For the loading time, I apply a loading time equal to 0.1 second. So that means I apply 10 cycles per second. So what he mentioned here, he said, you are not going to gain any more healing if you are applying very high rest period. He says once you apply a rest period 25 times the loading time, so in my case, if I'm applying loading time 0.1 second times 25, this is equal to 2.5 seconds. So he's telling me that if you are having a rest period equal to 2.5 seconds or more, you are not going to gain any more healing. The full healing, as I mentioned earlier, will happen by applying 2.5 seconds. Mena Souliman in 1961, he also did or came up with similar conclusion. He said increasing the rest period from 1 second to 19 seconds, he didn't have any improvements in fatigue life. So he tried, let's say, 0.5 seconds rest period, 1 second, 2, 3, all the way to 19. And he said, I think by 1 second, it's more than enough to have clear or full healing. Rathke and Sterling, also 1972, they mentioned that there is no significant increase in the fatigue life if we use a rest period more than 10 times the loading ratio. So that means 1 second. If you apply 0.1 second loading, that means maximum 1 second you will gain full healing. Van Jett, also 1977, he mentioned that there is an increase when he increased the rest period, the fatigue life can increase up to 10 times, from 1 to 10 times. This is one of my favorite quotes because this is strengthened my hypothesis from the beginning that the endurance limit changed. So what Stu and Singh they did, they show an improvement in fatigue life when they apply a rest period. And this improvement was from 0 to 25 times if you are not applying any rest period. But they say this improvement that can be from 0 to 25 times will depend mainly on the mix type and the test conditions. So the endurance limit is not constant. It's going to keep changing by changing your mix design or the testing conditions. And lastly, Castro also, he conducted the fluxural beam fatigue test with and without 1 second rest period, and he had an increase in the fatigue life up to 10 times. So done with the literature, now I know exactly what's going on, what other people did, and now I was confident to build my statistical program or statistical experimental design. So I used 6 factors. I'm calling it 6-factor fractional factorial design with partial randomization. So six factors because I'm having 6 factors that I'm considering in my experiment. Fractional factorial. When I say fractional factorial, it's not full factorial. I'm not testing every single combination because otherwise I'm gonna finish my Ph.D. in 20 years. And the last part, partial randomization. When it comes to preparing the samples, the testing samples, it's very hard to keep randomizing full randomization. When I say full randomization, I keep picking randomly from all over. And instead, we decided to finish one binder at a time. Which means the binder type, because there are several binder types. The one that we use in Phoenix is different than the one that we use in Flagstaff. So I finished one binder at a time, and that's how we call it partial randomization. So this is my statistical experiment plan. As you can see, there are different binders, different airboys, different binder contents, and again, those are the missing cells because of the partial fraction factorial. Even though I still had to test 288 samples. So I started that in September 2009, and I finished them this year, I think, April. So to give you some perspective of what are the sample dimensions that I'm using, this is the mold that we fill the pavements inside. I fill it in 2 lifts, and then we have, I don't know, it's not that clear here, we have a dynamic piston that compacted to the required air void. So in terms of now, I finished the statistical design and I need to do the testing itself. So in several school of thoughts, they try to study the fatigue from different perspectives. So here, as you can see, there are, here I just collected 6 different fatigue tests that people do all over. The first, this one here is the uniaxial test. This is the one that Walid is doing to get the endurance limit based on this test. But my favorite one is this. The 4-point bending beam test. So why I'm saying it's my favorite, again, it's a very standardized test. It has been there for 30, 40 years. There's a procedure, 2 procedures, national procedures, one for the AASHTO procedure and one for the HTM. So I guess now you know the advantages is everyone knows how to deal with this test. It's very well known, understood. But the disadvantages, again, it's time consuming. You need to do a lot of testing to be confident of your conclusion. So that means it's going to be expensive as well. So now going to the